In nature, we could produce signals like this sinusoidal wave function right here. But it happens that in digital systems like our computers, instead of working with this kind of continuous functions, we work with discrete functions since our memory space is limited. And that said, even though we have this input signal right here, we come at regular intervals and pick some of the values. So we could pick this value, then we pick this value at regular time intervals actually. So we pick this, we go to this next, we pick, and we have all this, which now gives us this kind of output right here. And from this we could define the sampling rate, which happens to be the number of picks we make per second. So like in this case, if we suppose that this is from this to this is 1 second, then counting this number of picks, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 picks in 1 second, and the sampling rate is 16 hertz. That said, instead of working with a continuous or with this Fourier transform for a continuous function f of t, this is now modified to give us our discrete Fourier transform, which is f of n, and then k varies from 0 to n minus 1 such that we have n samples. So it's just like picking n different points actually, because as we have said, for a continuous function we could afford to work with from negative infinity to positive infinity, but for our digital systems we work with a fixed number of samples. So if you notice, the formulas are quite similar. Here we have f of t, here f of k, e to the negative I 2 pi n, so and then k divided by n. Also note that after going through the discrete Fourier transform, if we have this kind of results, say we have negative omega 0 and then omega 0, it suffices to take just this right hand side, since basically the right hand side and then the left hand side contain the same information, which is that of saying that the signal whose Fourier transform has been calculated contains a frequency omega 0. So it's needless working with this, with all this, or with this two data points when just this one contains already all that information. Now if we have many more points, say omega 0, omega 1, omega 2, yeah, negative omega 0, negative omega 1, negative omega 2, it will suffice to just work with omega 0, omega 1, and omega 2, since they already contain all that information. In practice, we don't just take or get this input, for example, and then compute this discrete Fourier transform to be used maybe for input into our model. What we instead do is we break this up into several windows, and that's why we define this short time Fourier transform. The short time Fourier transform is defined such that we include a window function which actually functions for a given time or for a short time, and it just picks out a particular portion of our input signal. So here we have this window function right here, then we still maintain the f of k and this. So practically is the same thing, but with the difference that we have a window which is included, and we have this m right here. So we could consider this, for example, to be a window. So if we have this as a window, it's like our value when m equals 0. So when m equals 0, we'll now get s of n for the different values we could have for n. So we have s of n, and since m is 0, this point we have just f of k. So we have w of k. That's actually where we get this. We have w of k, f of k, e to the negative I 2 pi n k divided by n, which is similar to what we had here. So in this case, we just have something very close to this, and that's because we're working in this first portion of our signal. Now what goes on next is, after taking this and obtaining its transform, we now hop to the next window, and this hop size here is actually a parameter which is generally a function of this frame size or of this window size we have here. So this is a window size, and then this is the hop size. So the way we design this hop size is to ensure that these two actually overlap. So we have that. Next, we hop to the next position, we hop to the next position, we hop to the next position, and then we have the different values for our S, such that our M is varying. So we left from 0 to 1 to 2 and so on and so forth. And notice that this, you see here, right here, when M is equals 1, now we have K plus H. So we hop from K to K plus H and so on and so forth. So that's it. Once we have this, we could come up with this spectrogram right here. Now the way we get the spectrogram is by simply transposing for each of these windows their discrete Fourier transform or their fast Fourier transform. Note that the fast Fourier transform is a more efficient implementation of the discrete Fourier transform, which makes use of certain properties of the signal in the complex domain. And also the value of n when working with the fast Fourier transform is in powers of 2. Now that said, if for this frame or for this window we have our discrete Fourier transform, we transpose it. So as you could see right here, we have this cut. You see, notice that they have these different cuts here. So for this, for the first frame, we obtain this discrete Fourier transform and then we transpose it such that, because first of all we have this time here, but after obtaining this discrete Fourier transform, we're going to instead have the frequency in this direction. We're going to have frequency and then amplitude. So what we do is we transpose that such that we have now the frequency, as you could see here, and then the amplitude will be represented by the color map we get here. So this very intense colors here tell us that this signal for the very first frame sizes or for the very first windows has high frequency. So as you can see here, we have this high frequency, and then we go to the next frame, just like this next frame right here. We obtain this DFT, then it's FFT. We transpose that, we have the frequency, so we have the frequencies, and then we have the for a given time, and then the color represents the amplitude. Then what we do is we simply repeat this all through, and then we now have our spectrogram, which is now ready to be fed into our model. Let's take this example right here. We have the sine of 2 pi, that's 2 pi times 400, 2 pi times f x, plus the sine of, for now let's comment this region and then run this. Now here we have the fast Fourier transform, which is gotten by the tf.signal.rffT. Now this RFFT actually means the real fast Fourier transform. Then once we get the fast Fourier transform, we shall simply plot this out. The reason why we're doing this is because we want to actually be able to plot this out. So right here we have the signal. Recall our signal's frequency is 400. Now after going through the fast Fourier transform, we see that we have this peak at 400. Now the next thing to do is we shall do this, run it again, and there we go. We now see that when we include these other signals with sort of frequencies right here, we have this value. See, we have 900, we have 400, and then we have 20 right here. So this was just to permit us see clearly what's going on. With TensorFlow, you don't need to go through all those steps. All you need to do is to pass in the signal. So we have our signal, you just pass in the signal, you specify the frame length, and then the frame step, which is actually the hop size. You see that's a fraction of our frame length. Let's consider a frame length of say 10,024, hop size of a quarter. Okay, run it. And here's what we obtain. We have this, we see the signal, we have a fast Fourier transform, and then we have a spectrogram. Now notice that unlike the other spectrogram we had seen for the audio signal, here we have this fine lines which cross through all the time axis. And this is simply because for each of the frame steps or windows, the frequencies contained in the signal remain the same. So as we go, let's take for example just one of this. So for this, for example, we see that since our frequency is 400, we have this. From here, we see that the value of the frequency actually remains the same and remains constant all through the signal. And it tells us that the signal is a pure sine wave. Now, if we add this up, here's what we get. We see that for each of the frame size, that's for each of the window sizes, we have the same frequencies all through. Now also notice that we have some bands. So you have this band right here. You can see this band, you can notice this band, notice this band, notice this, notice this, notice this, and so on and so forth. So this actually represents the frames. Now notice how once we reduce this, that size is going to change. So let's say we take a value of say 64 and yeah 32, run that. Okay, so you see that here this bands reduce and now this lines become very coarse. So unlike the previous line which were very fine, now the lines become very coarse. So as we reduce the frame size, the frequency resolution drops, whereas the time resolution is increasing. So we see that we have more finer frames as compared to what we had previously, but the frequency resolution actually drops. Now let's get back to this. We have this, run that again, and there we go. We see how the frequency resolution now increases as we increase the frame size. So this is a parameter which you can actually change and then see how well the model performs with respect to each of this, or with respect to changes in this parameter. So here we have the frame size and then we have the hop length. We now prepare our data for training. We have the path to the audio files and then we have the path to the CSV file which contains all the audio transcriptions. Right here we create this dictionary and then we go for each line in this audio file, in this CSV file. We are gonna put in the transcription. So like here for example we have this line in F. We pick out the transcription, that is, first of all we pick out the file name, that is I, we convert it to a string, and then we have this, and then the transcription is this text, which is this one. Notice that the file name and the text were split or divided by this character, and that's why we do a split like right here. So run this and then we print out the audio text dictionary. And here is well obtained. We start from the beginning. We have printing is the only sense. So here we have the file name and then we have its transcription right here. Could go right to this. We have the file name, its transcription, and so on and so forth for all the different files we have in our data set. We now go ahead to define our get spectrogram function, which takes in a file, and then we use TensorFlow's io.read file to read this file. We now decode the audio using this decode audio function right here. What it does is simply takes the audio binaries after we've read the file. It now applies the decode wave function because our files are wave files. So we have this decode wave function which takes in the binaries and then outputs the audio. Then we squeeze this so that we convert our output to the required dimensions. Now once we have that, we have the waveform. Then we apply the zero pattern where this is somehow like the maximum. Now the reason why we're having this is because we've collected, or we took out the audios, and then the audio with the highest waveform dimension actually had this dimension. So anytime we have a dimension less than this, we simply apply the pattern. As you can see right here, we just have those zeros. So depending on the waveform's length, we take this maximum minus that, we get the rest. We have the zeros and then we apply the pattern. by concatenating the waveform we obtain from this with that zero pattern. Then once we have that, we now pass through the spectrogram. Now we obtain the spectrogram by passing through TensorFlow.signal.short time Fourier transform. We specify the length, and then we specify the frame step right here. We have the spectrogram. We apply this function which collects just the magnitudes, because the spectrogram will contain the magnitude and phase information. So since we're interested only in the magnitude information, we simply get the magnitude of the spectrogram, because what we get from here is going to be a complex number. So once we have this, we now return our spectrogram. We add this dimension. We shall see later on why we needed to add this, because we are having a model which is having convolutional or 2D convolutional layers in its earlier stages. So it's important that we have this, or we add this extra dimension. Now once we have that, we could now get our spectrogram. We could print out our spectrogram right here. Before that, we could also print out the waveform we obtained, so we could see exactly what we got. So we have the waveform.shape, and here we have our spectrogram.shape. So there we go. We have this waveform of 219,293 data points, which now generates the spectrogram of dimension 6,955 by 33 by 1. This one was just included, as we saw right here, this last dimension. Normally it's this, actually, since we're having a 2D figure. Once this is done, we could go ahead to plot. So basically we have this. We start by doing this transpose. Recall the reason why we're doing this transpose is because we want the frequencies to take up the y-axis and then the time take up the x-axis. Once that is okay, we now simply plot, as we've seen previously, with this color mesh, where it's going to make sure the magnitude is going to be represented by the colors, and then in the y-axis we have the frequencies, the x-axis we have the time. So run this, and that's what we obtain. We see how, unlike the pure sound wave where we just had one line going through, now we have this different patches, and that's because for each of the time frames there's actually different frequencies present in the signal. So this is kind of what we obtain. Note that this is a power spectrum, which is kind of like a conventional way of visualizing this kind of data. Let's now look at our output labels. Supposing we have this input and then we have this as output. After going through a spectrogram, or after obtaining the spectrogram, this is what we have. This tensor of dimension batch size by the time dimension by the frequency by 1. Now once we pass this through our model, we obtain an output which is meant to be of dimension batch size by maximum transcriptions. Now this maximum transcriptions is the maximum number of characters we have in the outputs. So this kind of prediction, for example, has just 168 characters instead of maybe the maximum, which is 192. Now note that unlike previously where we're working with word tokenization, now we're dealing with character. So each of those characters actually represent a token in our vocabulary. Now coming back to the code, we have this label, so we get the file path, and then we simply obtain this label from it. And this is done making use of the dictionary, which is the audio text dictionary we had created previously. Because this audio text, recall, if we have to, let's print this out right here. If we print out our audio text, you'll see that each of this were matched to a label. So basically what we're doing here is we obtaining that file path. From the file path, we're obtaining that file name, and notice how we take off the dot wave by doing this, because when we, let's print this out. So if we print out file path right here, you'll see, modify that, you'll see this is what we obtain. Now what we're interested in is getting just this, so that with this, for example, we can match it up with a label, and that's why we have the, first of all, we use the os.path.base name to obtain this base name, which is this, and then we select just the path before the extension. Now once that is done, we now have our label, and then we could output that simply. So right here we return the label, then we obtain the label from this, and then we could print out the label. So let's do that. That's fine. We'll run that, and that's what we obtain. We obtain the spectrogram, and then we obtain the label. Then next we go ahead to define the vocabulary like this. We define this vocabulary such that we take into consideration the fact that we have spaces, we have the unknowns, we have the full stop, we have comma, question mark, and then we have all the characters from A to Z. So basically, if we have this, if we do this, for example, 9 let's say 1, we obtain this character. Now if we have 96, we have that. 97, we obtain A. Now 97 plus 26, or rather plus 25, we obtain Z. So this is how we obtain all the characters from A to Z, and that's how we construct this vocabulary. So that's how we run this, and we see that we have our vocabulary right here. Now the reason why we're putting this pad at this level here is because the way the CTC loss functions, which is what we are going to be seeing shortly, the way it functions actually is such that it wants the padding to take the last position in the vocabulary. So the way it has been configured influences our choice of the padding's position to take up this last position right here. So by doing this, we've simply created our vocabulary, and we have a vocab length of 32. Then we go ahead to define this get label function, which takes in a label like this one and then generates an output based on the character position in the vocabulary. So this A, for example, you see it matches up with this position right here. Notice how we lower all our inputs or our labels so that we don't get to create vocabularies where we have a big A, small a, big B, small b, and so on and so forth. So that's why we have this lowering right here. Then we have the get vocab, which is defined such that for every character we're able to obtain its corresponding index in our vocabulary. So we run this get vocab, and then we have the get label. Let's, for example, take this. Suppose we have this, so let's have the label. Let's take this label we had from here. So we'll run that label, we'll run it again. We see that we have the shape 168, and then for each of this, say we start with A, we have 0, 1, 2, 3, 4, 5. So we see it matches up. The next 18, and so on and so forth. So that's how it works. And then we now move to the data generator. We can see here we have the get spec, which gets the spectrogram and its label. Then what we do next is we append this into our X, that's our inputs. The label, we obtain the get label, we append it to Y's, and that's all. So basically it's what we've done already. So we'll run this. We now define the train path, the batch size, the sequence length, the vocab size, learning rate, number of epochs. Then from this, now we have the data generator, which is created right here. We have the train path, the batch size, and all of that, which is passed in. For now, we are not going to have or work with the validation, so we just have this. So we'll run this 3,